get cations works. This is one way. And so this can actually work rather nicely too. So the Friedel-Crafts alkylation is still very, very useful, even though it can lead to skeletal rearrangements. Now there's another limitation for Friedel-Crafts alkylation, and that concerns polyalkylation. In other words, you add a methyl group through methyl chloride, aluminum chloride, and then a second one, a third one. I kind of hinted that that might be a problem last time. So with the Friedel-Crafts, it is a problem. And so the reason it's a problem is that each subsequent addition of methyl is faster than the first. Okay, so the first step is slow, and then the second one is faster, and then the third methylation is faster yet, and so on. And so, excuse me, and so that being the case, how do you stop the reaction at step one? Well, the way you do that is you use an excess of benzene. Okay, so if I use a whole lot of benzene and a little bit of this, then I don't have a chance to do the second and the third alkylation because there's more benzene than electrophile. That works, but it's a problem too, because now I have to separate the excess benzene from the product. And how do you do that? Well, if it's toluene benzene, you do that by fractional distillation. But it's a nuisance, right? So yes, you can get around that by using an excess of a reagent, but that can be problematic. But the issue here, and we'll come back to this in a few minutes, the issue here is, why is it that the first step is slower and the second one's faster and the third one's faster yet? We'll come to that in a minute. Okay, so that was the Friedel-Crafts alkylation. And it's an alkylation, meaning that you're adding an alkyl group to the benzene ring. Now, there's another Friedel-Crafts reaction, probably more important, more useful, called the Friedel-Crafts, not alkylation, but acylation. Now, this group here that I have the red line around, this is an acyl group. So any kind of group like this is an acyl. So carbonyl with R, acyl, or R is carbon something. Okay, that's an acyl group. So you start with acetyl chloride. That's this species here, where I have a chlorine attached to the carbonyl. You treat that now not with catalytic, but with stoichiometric aluminum chloride. You'll see why. With the Friedel-Crafts alkylation, we could get away with catalytic aluminum chloride. Here, you actually need a full equivalent, and the reaction doesn't work. We'll see why in a minute. And so you use a little bit of an excess, maybe 10% excess. That's what that 0.1 equivalence is doing. And then you decompose the product with water, and you end up with essentially quantitative yield of acetophenone. That's what this stuff's called. Now that's very nice. And by the way, the Friedel-Crafts acylation, it stops after the addition of a single acyl group. You don't have to worry about polyacylation. So unlike the Friedel-Crafts alkylation, this one stops after the first step. Okay, now the reason you need excess of this is that the product, and I haven't highlighted it here, maybe I should highlight it, but the product, just like the starting material, has non-bonding electron pairs on the oxygen atom. However, the non-bonding electron pairs in the product, these, are more basic than those, and so this is a basic species, so it reacts with the Lewis acid and forms this stable complex. That takes the aluminum chloride out of circulation, and so that's why you can't use it as a catalyst. You need a full equivalent of aluminum chloride because the product reacts with it. Now let's go back and see why this should be more. Why should this electron pair be more basic than that one, you suppose? Well, it has something to do with the fact that I have a carbon-chlorine bond versus a carbon-carbon bond, right? What do we know about carbon-halogen bonds? We know they're polarized, right? They're polarized with the negative end pointing at the halogen and the positive end pointing at carbon. So when I have a acyl chloride like this chlorine is pulling electron density out of that carbon atom, and in so doing is also pulling this electron pair towards the chlorine. So this electron pair is no longer as available to bond with aluminum trichloride, in the acyl chloride is much more available here, because here I don't have an electron withdrawing chlorine group making it unavailable. And so the product is a stronger Lewis base than the starting material. Weak Lewis base, strong Lewis base. So strong Lewis base reacts with the Lewis acid and ties up the aluminum trichloride. So the reason you add water is to decompose this species at the end of the reaction. Okay, so at the end of the reaction, you don't get the acetophenone. You get the acetophenone aluminum chloride complex. That has to be decomposed with water, give you aluminum hydroxide and HCl, and the organic piece. Okay. So what's the mechanism for this? The mechanism here is maybe a little bit different than what we saw for the Friedel-Crafts alkylation, but as you'll see, not that different. Okay, so what goes on is this. You have electron pairs on chlorine, right? So you know the chlorine is also a Lewis base, not just the oxygen. And so the aluminum trichloride bonds to the chlorine, polarizes that bond. At some point, you end up breaking this carbon-chlorine bond, like so. Okay? At that point, we have aluminum tetrachloride and an acylium ion. Now, this is not a stable species, but it is resonance. It does have two resonance forms. Of the two resonance forms, which one do you suppose is the more important? The one on the left or the one on the right? Think. You already know the answer. Yeah, the one on the right, because the one on the right, even though it places a positive charge on an electronegative oxygen atom, all atoms in the right-hand resonance structure have complete octets, right? So this is going to be the important resonance structure. Okay, so this is a very, very powerful electrophile, and it reacts with benzene ring. I've shown all the steps. You form that intermediate, you lose a proton, and you end up with the ketone as your product. Okay, so let's go back to this. So you form the ketone. So I've shown the aluminum trichloride reacting with the electron pair on chlorine. But I just showed that we have electron pairs on the oxygen too. And so why does the aluminum chloride bond to the electron pairs on oxygen? Is there anything that says it doesn't? The answer to that's kind of a tricky question. The answer to that is sure it does, but it's reversible. That doesn't lead to product. And so if it does bond, that won't give you an acylium ion. And so at some point, it has to, in order for the reaction to proceed, it has to react, the aluminum trichloride has to react with the chlorine. So the interaction of the Lewis acid with the Lewis basic electron pairs here is reversible. And at some point, this happens. Once this happens, it's irreversible and goes to the product. Okay? Now the nice thing about this is that you can do it intramolecularly. And so the intramolecular case is very, very nice because it forms rings. And so you can, and I've shown the reactive conformation, if you will, of the acid chloride on the left. The ortho positions clearly have to be unsubstituted. In other words, I have to have at least one ortho hydrogen for the reaction to take place, otherwise no reaction, right? So here I've got a hydrogen here and a hydrogen there, no problem. So I can form the acylium ion, then the benzene ring attacks, I form this bond, and so on. And I can form rings like that in very good yield. So with the Friedel-Crafts acylation, you don't get polyacylation. So if there's a second acylation that's going to take place, that second acylation is slower than the first. So with the Friedel-Crafts alkylation, second reaction faster. Friedel-Crafts acylation, second reaction slower. Don't memorize it, you're going to understand it in a minute. And so let's recap now some of the stuff that we know for making carbon-carbon bonds. Remember last time I said Friedel-Crafts alkylation was an important reaction because why? Because it's one of the few ways that we know to make a carbon-to-carbon bond. So let's review and see the ways we know to make carbon-carbon bonds. So one way is to use a carbene to form a cyclopropane. The other way is to use a Grignard reagent. Remember we talked about these. and add to a ketone to give a tertiary alcohol. The other is to form an acetylide. This was the acetylene chapter. And this is a nucleophile, a carbon nucleophile. You can do a displacement that way. The others deals all where we form 2 sigma bonds, and now the Friedel-Crafts. Now there's another carbon-carbon bond reaction that I've left off, and you will recognize that in a minute. Let's just take this bromide, okay? And let's do a reaction with cyanide. So if I do this kind of reaction, what do we call this? I formed a bond from this CH2, that bond there, to the cyanide. So that's the bond that I formed. That's a carbon-carbon bond too. What kind of reaction is this? Elimination. Ouch. SN2, right? This is just a SN2. Oh boy, don't forget SN2 reaction. That's a substitution reaction, right? I'm substituting the bromine with the cyanide. There's an elimination. I'd use some kind of strong base, maybe potassium cubic oxide, and I would get elimination of HBr. So I'd end up with potassium bromide, and the hydrogen would be bonded to the cubic oxide group. Okay, so that would be an E2. So SN2E2. Don't forget that. This is important. So getting back to carbon-carbon bond forming reactions. This is another carbon-carbon bond reaction that we know. This is an SN2 reaction. This is also an SN2 reaction. It's just that the nucleophile here is an alkyne, so a carbon-carbon triple bond. Here, it's a carbon-nitrogen triple bond with the negative charge on carbon. Okay, so the two are related. So these are all the ways that we know now to form carbon-carbon bonds. So we know a fair number, 5, 6 different reactions, right? Okay, so now let's talk about directing effects. And directing effects will also kind of alert us to this business of why you get polyalkylation and you get monoacylation. So up to now, we've talked about simple aromatic substitution reactions, simple in the sense that the benzene ring was unsubstituted. Okay, so you start with a benzene ring, treat it with an electrophile, you get a product. The question arises, don't start with benzene, start with a monosubstituted aromatic, and what happens? And actually, something interesting happens. Look, if you start with bromobenzene, where you have what? You have a single substituent on the benzene ring, bromine, and then you want to do a nitration. Remember that for the electrophilic aromatic nitration, you need nitric acid and a catalyst. The sulfuric acid is a catalyst because it generates the NO2+, the nitronium ion, that you need in order to do the Friedel-Crafts, or the acylation reaction. And so this is a very weird reaction because the nitric acid is acting as a base. It's getting a proton from the sulfuric acid, losing water and giving you NO2+. That NO2+, you'll notice, ends up either para or ortho, but hardly any of it ends up meta. So there seems to be a real preference for either the ortho or the para product. And so the meta isomer is hardly formed at all. So it looks as if the bromine directs the substitution to take place either ortho or para. So that same ortho-para directing effect that you see with bromine, and NO2 will be seen with every other electrophile. So if we did a nitration, it went ortho-para. If we did a Friedel-Crafts reaction, it will go ortho-para. If we did any other kind of sulfonation, it will go ortho-para. So that ortho-para is not specific to the electrophile, it's specific to the bromine. So it's not because of the nitro group, it's because of the bromine. Okay, so bromine's doing this. Okay. And now you contrast the behavior with what happens if I do it the other way around. So I had a phenylbromide, bromobenzene, I'm nitrating. Now I take nitrobenzene and I brominate it. Okay, so I'm just doing it, I'm introducing the bromine second. If I introduce the bromine second, then I only get the meta isomer. So what that means is that if I want to get the ortho-para isomer, then I start with bromobenzene and I introduce NO2. If I want this compound, which is only formed in tiny, tiny amounts, I can get that, and I can get it as the exclusive product, but then I have to start with the nitrobenzene and do the bromination in the second step. And so it looks as if we have two classes of substituents on aromatic rings. We have those substituents that are ortho-para-directing, like bromine, and then we have other substituents, like nitro, which are always meta-directing. And what I said before is true here too. It doesn't matter that you're using bromine. Any other electrophile that you use always will go meta. And so it's not the electrophile that is responsible for the meta substitution. It's this group here that's doing. So the nitro group directs meta. Okay, now that's just what I said. Substituents on the benzene are either one or the other. They're either orthopara or meta. They're not orthopara sometimes, meta the other times. No, orthopara all the time or meta all the time. There's a table, this is the 5th edition. Take a look, they have a list of substituents and whether they're orthopara or meta directing. And and you don't have to memorize those, but it's a good idea just to take a look. Now, the general trend is going to be this, that if you have a group that is electron withdrawing, like the nitro group, then that's always going to be meta-directing. But it's going to be doing something else, too. It's going to be deactivating the ring. So in other words, think of it this way. You're doing an electrophilic aromatic substitution. In other words, the benzene ring is donating electrons to an electrophile. Now, if I take that benzene ring and I stick a nitro group on it, the nitro group is pulling electron density out of that ring. That means that that ring is not going to be as good a nucleophile. It won't react with electrophiles as fast if it has a nitro group attached. Why? Because the nitro group is competing for electrons. And so meta-directors are going to be electron withdrawing, and they're going to deactivate the ring. Deactivate the ring just means that the reactions of, say, something like nitrobenzene are going to be slower than those of benzene, because the nitro group is pulling electron density out of the benzene ring. It's deactivating it. It's deactivating it, and it is meta-directing. Electron donating groups are going to be activating for the same reason, because the electron donating, that means that the benzene ring has a surfeit of electron density to react with electrophiles. And so electron donating substituents are going to activate the ring, make it more reactive, it's going to react faster, and at the same time are going to be orthopara-directing. So if it's electron withdrawing, meta and deactivating. If it's electron donating, orthopara and activating. Now, having said that, there's a small exception, very tiny exception. The exception are the halogens. And so fluorine, chlorine, bromine, iodine, these are always orthopara-directing, and we saw that for bromine. They are slightly deactivating. They are not, I mean, fluorine, of course, more deactivating than the others. Now, why should the halogens be an exception to the rule? The rule kind of made sense, and now I said that, well, there's this exception. The exception is because the halogens all have non-bonding electron pairs. And those non-bonding electron pairs can overlap with the pi electrons of the benzene ring. And so, as a result, the halogens do this. They're kind of push-pull substituents. Let me see if I can explain that for you so you can understand it. Okay, so let's just take bromobenzene, the one that we just saw, okay? And I'm going to purposely not show the non-bonding electron pairs. You'll see why. So I have a carbon-bromine bond. That bond is polarized, right? You know it's polarized because bromine is electronegative compared to carbon, which means that there's a positive end to that dipole and a negative end. Positive end here, negative end. So the positive end of the dipole is sucking electron density out of that ring, right? So what that tells you is that the bromine is pulling electrons out of the ring towards itself. That's deactivating. But this operates through the sigma bond. Sigma bond polarized, polarized, and deactivates. Okay? Everybody agree? Now, let's redraw this. And this time, let's show the electron pairs, okay? Now, those electron pairs can overlap with the benzene ring. So I can show the electron pair doing this, okay? And that is a resonance structure for that ring. And I won't show all the resonance structures, of course. But I will have a negative charge there, and I'll have a positive charge there, okay? So this makes it look as if this is operating through the pi bonds. It is a resonance effect, and it activates. So this is the pull, and this is the push. Okay, so it's pulling electron density out through the sigma bond, but it's pushing them back in through the pi bond. Guess what? Sigma bonds aren't very polarizable. Pi bonds are. Why are pi bonds more polarizable than sigma bonds? Well, because they're further from the nucleus. You knew that. So what that tells you is that yes, this is going to deactivate the ring, but this is going to be a stronger effect. And so that's why the dual nature of these halogens. Yes, they deactivate the ring a tiny bit, but they still are ortho-para-directing because of these resonance structures. So that's why. So know that all the halogens have non-bonding electron pairs, and it's because of what I showed. Now, to understand these trends, to understand why electron donators are ortho-para-directing and activating, and why meta-directors are deactivating, we need to show the resonance structures for all of the intermediates, okay? So let's take a strongly activating substituent, which is methoxy group, and I've highlighted the electron pairs on oxygen. And now let's just show, the electrophilic aromatic substitution. What's E plus? Doesn't matter, because whatever electrophile it is, the trend isn't going to change. So we don't care what the electrophile is; it's going to be the same regardless. So we form these resonance structures. Now, again, when you go home, you need to be able to reproduce this. Okay, so make sure that you know how to draw resonance structures at the end of this. You'll notice that there are 3 black ones and 1 red one. And the red one is, of course, going to be the important one, because why? Why is the red resonance structure the most important one of all 4? Because everything's got a complete octet. Yeah, you're right. Okay, so when I have an electron donating group here, and when the electrophile comes in para, I get this very nice resonance form that I don't get if it goes in meta. Ortho has the same kind of important resonance form, another red one, where everything's got an octet. I haven't shown all the others, okay? So as long as it's ortho or para, I end up with one of the 4 resonance structures that's very important, very stable, and has a complete octet. Now, convince yourselves that when you do the same kind of substitution meta, you end up with 3 resonance structures, no red one, and no one where all of the atoms have complete octets. And so again, what that tells you is that in the meta case, you have 1 less resonance structure than orthopara, and you lack the exceptionally stable structure where all atoms have complete octets. So the reason that you end up with orthopara substitution and not meta substitution is because the stability of that intermediate is reflected in the energy of the transition state, Hammond's postulate. And so you can show this, again, using these reaction diagrams. So if it's para, you have a lower activation energy. If it's meta, you have a higher activation energy, because here you're lacking one of the resonance structures that you have in this form. And so the more stable the intermediate, the lower in energy, And so the faster you form para or ortho substitution, and the slower you form here. So the activation energy is larger for meta. And so very simple argument, easy to see, drawing resonance structures. That's the situation you have for ortho para. So now the question is, well, okay, that's fine, you know, maybe I believe that, but what about meta? So now we have to do the same, we have to go through the same exercise, but with meta substitution, and see why it is that electron withdrawing groups don't direct orthopara, but direct meta. So let's try that. So the electron withdrawing group we're going to pick is the one that everyone likes to use, nitro, and we're going to show meta substitution. And so meta substitution results in these three resonance structures, okay? So positive charge here, positive charge there, positive charge here. Now, if you look at the para substitution, what would happen with para substitution? You get this as a resonance structure, which puts the positively charged carbon directly adjacent to the positively charged nitrogen atom. And so what that tells you is that this is going to be no good. What does no good mean? Well, no good doesn't mean it's been bad. It means that it's high in energy. Okay, so in other words, placing those two positively charged atoms adjacent to each other is going to cost you a lot of energy. What that really means is that this resonance structure is unimportant. That this doesn't count. So in other words, as if I only have two resonance structures. So here I have three resonance structures stabilizing this intermediate. For the para substitution, I only have two. Why do I have three? Well, because this one doesn't count. This one doesn't count because high in energy, therefore not important. These are all about the same in energy. Okay, so effectively, you only have two resonance forms for para or ortho. By the way, I didn't show ortho. Ortho is exactly the same. If you don't believe me, go ahead and work out the resonance structures for ortho. You'll find that one of them places the two atoms, the two positively charged atoms adjacent. That one's no good, so you effectively only have two for ortho or for para. And so the intermediate, this intermediate, is higher in energy than this one. Now, the important thing to remember is that both intermediates, both this one and this one, both of these are still higher in energy than they are for benzene, right? And much higher in energy than they are for methoxybenzene. Because in benzene, I don't have anything pulling electron density out of the ring. In methoxybenzene, I actually have a methoxy group pushing electron density into the ring. So even though you end up with meta substitution and no ortho and para, this meta substitution product is formed at a slower rate than the corresponding electrophile rate with benzene would be. So benzene is going to be faster than this reaction. So intermediate for meta is more stable than ortho para, but it's less stable than the intermediate for methoxybenzene and also less stable than the intermediate from benzene. So inductively, the nitro group removes electron density. So the nitro group is electron withdrawing from the benzene ring. Benzene ring in nitrobenzene is not as good a nucleophile. It doesn't have electron pairs as available for bonding to the electrophile, so the reaction is slower. Okay, so at this point, we've kind of explained why it is that electron donating groups give you orthopara and why electron withdrawing groups give you meta. But one thing we didn't explain was why it is that we see the ratio that we see for orthopara. So let's take a look at that one again. I didn't say anything, so maybe you noticed, maybe you didn't. Okay, let's go back to this first example. How many ortho hydrogens do I have? How many ortho positions do I have? Ortho to the nitro, to the bromine part. 2. How many para? 1. 2 to 1. So if it's a statistical ratio, I should get 2 to 1. Instead, it's almost 1 to 2. what gives? Okay, now you don't see any, what this is, you know, what is clearly not the case is that the resonance structures are somehow skewed one way or the other. No, that's not it. But there's this very, I mean, you can't argue with experimental fact. Even though the statistical ratio should favor this product over that one, actually this one is favored over that. Why might that be? And you see that, you know, you see that a fair amount. So for orthoparadirecting groups, why don't you always get a 2-to-1 ratio of ortho to para? You don't, right? I mean, so the 2 protons ortho, 1 para, statistical ratio is usually not seen. It's van der Waals repulsion. Look, if this group is big enough, then van der Waals repulsions are going to strongly disfavor the ortho substitution, because that electrophile, especially if it is also large, is going to bump into, so to speak, that methoxy group or whatever is at the ortho position. And so, for steric reasons, the para substitution should be always favored. And you often see that. On the other hand, if this group is small enough, like methyl is pretty small, then you do see the statistical ratio. And so here the activation barrier is very small because this is electron rich and this is reactive. Methyl group is small, so here, in fact, you do see the statistical ratio. But in many cases, in most cases, you won't. You'll see a ratio that's skewed to favor the para product just because of the van der Waals problems that you encounter. Okay? So, yeah, so you need to kind of think about more than just the stability of the resonance structures. Okay, so at the risk of beating this to death, let's talk about activating and deactivating substituents. I think this is probably pretty obvious, but let's make sure. When we say activate, or when we say deactivating, or faster, or slower, or whatever, the question you guys always want to ask is faster compared to what? Deactivating compared to what? Activating compared to what? So what's the point of comparison? And here, the comparison point is always going to be benzene, no substitution. So that's our point of comparison. So when we say that methoxy groups, or methyl groups, or electron donating groups are activating, it is activating compared to benzene. Okay, so benzene is your point of reference. Meaning that if I have a methoxy group on the benzene, that all electrophilic substitution reactions, that methoxy benzene, are going to be faster than the corresponding reactions run under identical conditions with benzene itself. Okay, so deactivating, same thing, right? And now, I've already done that kind of with this example. Okay, so here what I tried to do is I tried to dissect the inductive effect, which is the pull, from the resonance effect, which is the push. Okay, so inductive effects operate through sigma bonds. Resonance effects operate through pi bonds. Resonance effects are usually stronger than inductive effects, and operate over greater distances. Okay, so inductive effects are fairly short range. So now let's take a look here. The same thing that we said about bromine being electron withdrawing. Well, the same thing's true for oxygen, isn't it? Because oxygen is electronegative compared to carbon. So really, there's an inductive effect of that oxygen that is pulling electron density out of the ring. But there's a resonance effect, too, that is putting electron density into the ring. So the two effects that the oxygen has, or the bromine, as I showed you a little while ago. One is an inductive effect operating through the sigma bonds pulling electron density out, deactivating the ring. The other is a resonance effect operating through the pi bonds, pushing electron density back into the ring. So this is the pull, that's the push. And of the two effects, the resonance effect is stronger, and it wins out. And so that's why methoxybenzene is an activating substituent and not deactivating. In other words, if the resonance effect were equal to the inductive effect, then it would be a wash, right? Or if the inductive effect were stronger than the resonance effect, then the methoxybenzene would be deactivating. But it's not. It's activating because the resonance effect is stronger than the inductive effect. And so, so resonance and inductive effects here oppose each other. They're working at cross purposes. One's pulling electron density out, the other's pushing electron density in. But the resonance effect overwhelms the inductive effect because pi electrons are more polarizable than sigma electrons. And so they are easier to, those pi electrons are further from the nucleus. The pi electrons are easier to deform, and so resonance effects are stronger. So something similar to that takes place with the halogens. That's the business of the bromine that I just talked about. And this is essentially the same that let's not go through all that. We've talked about that with the bromine. Now, with the case of nitro, the electron withdrawing NO2 group retards electrophilic substitution, but it retards it less when the attack is meta. So in other words, in all cases, whenever you have an electron withdrawing group attached to a benzene ring, in all cases, the reactions are going to be slower. But they'll be much slower for orthopara and a little bit less slower for meta, and that's why meta wins out. And so your text, I think, suggests that these groups be called not meta directing, but meta allowing. In other words, it allows the substitution. It doesn't direct it, it just makes it possible by not deactivating it too much to take place meta. It's a minor point. Okay, now, you kind of know where this next discussion is headed because of what we said earlier on. Let me remind you. Remember I said that if I start with bromobenzene and I do the nitration, I end up with these two products. But if it's this product that I want, I can't start with bromobenzene. I have to start with nitrobenzene and do the bromination. If I start with nitrobenzene, no bromine present, the nitro is going to direct meta. And so now I have a way to determine what substitution pattern on the benzene ring I want to build up. So somebody comes to me and says, I want you to make this compound for me. And you can now, because you know about these ortho and meta directors, you can figure out how to do it. So if I want this compound, this is the one I just showed you. Now, this is a meta-directing nitro group. The bromine is ortho-para-directing. But the two groups are what? They're para. And so what that means is that if I introduce the nitro group first, I'm screwed. Because then the bromine is definitely going to come in meta. However, if I introduce the bromine first, then I'm okay. Because that means the nitro will come in para and ortho. And so if somebody says, I want you to make me a kilogram of this, then you start out with your benzene first, brominate first. Now this is ortho-para-directing, and you end up with mainly this and a little bit of the meta, or the ortho, which you have to separate. You do it in the reverse order, as I pointed out, you're screwed, because the meta director coming in first ensures that you don't get the right product, that you get the meta. And so you have to know which one is ortho-para-directing and which one is meta-directing before you plan the work. So this This is a fairly simple case because you only have one substituent. But when you have multiple substituents, then it becomes really tricky, doesn't it? So these are, you know, they're real cases, but simple because only one substituent on the ring that you start with, or none. You only have to introduce two. That's not a problem. What happens? So we don't know how to solve all of the problems. Here's one you don't know how to solve yet, and that's this one here. How do I go from here, you know, put question marks? How do I go to there? So a way to do that, maybe we can think of? Not so easy, right? Because both of those nitro groups are meta-directing. So once you get one nitro group in there, the second one is going to be meta. It's not going to be para. And so there is a way to do that, but we're going to learn that much later on. The way you do that, I'll tell you what the logic is, and you'll see how, you know, it's logical how you do it. Look, the first thing you do, and I'm not going to tell you what this is, you put a substituent here, x. Okay? X will be an orthopara director. Screwed up. Okay, so yeah, it's about right. So you do this, and then you have to find a way to convert that into nitro, and that's how it's going to work. Okay, so yeah. So you start out with an orthopara director. That gives you the first nitration. Then you take that X group and change it into a nitro. You're going to see that somewhat later. So there is a way to do this, but right now, this is an insurmountable problem because both groups are meta-directed. So let's take a look at some other odds and ends here. Okay, so I have dimethylbenzene or metaxylene. And now the two methyl groups are what? Are they activating or deactivating? Yeah, they're activating, both activating. And both are ortho-para-directing, which means that this is activated, right, because that's ortho to both of them. This is activated because that's ortho to this one, para to that one. This is activated too, but the only part of the ring that's not activated is here. So both of these carbon atoms, you can expect reactivity, but these two are the same, and that one. Now, if I do a Friedel-Crafts acylation, guess what? This is about the only product I see. And so it looks as if these two positions are more reactive than that. But remember what we said about van der Waals repulsions. The two in the middle, that middle position, is going to be deactivated by van der Waals repulsions relative to the other two. So reactivity here is going to be slow because the electrophile, the acylium ion, is going to bump into two methyls. Here it bumps into only one. And so that's why you see this as your major product. So that kind of makes sense. Now, when you have a highly activated aromatic ring, so methyl groups activate the ring, but as you're going to see, hydroxy groups are really active, strongly activated. Methoxy groups are a little bit less so. When you have a hydroxy group, then it's very difficult to stop after a single addition. And so this is essentially an instantaneous reaction. If I have bromine in water and I throw in phenol, you essentially get all the two ortho in the para position brominated essentially instantly. This is a diagnostic test for phenol. So in other words, in the old days, before they had NMR and mass spec and all those wonderful tools, you had a sample of phenol. What you did was you threw it into bromine water. If it was a phenol, you see a quick precipitate of the tribromophenol, and that was a very good indication that it was a phenol that you had. Okay, so phenols that show that reactivity. There are a lot of diagnostic tests like that that have been developed that are kind of a lost art. Believe it or not, some of them are still useful today. There are times when you need to know those because for various reasons the instrumental techniques fail. So this is an example of a highly activated aromatic that you really can't stop after the first substitution. You can do it, but it's a bit tricky. Okay, so when you're adding nitro groups, it's very easy to do that one at a time because the first nitro group deactivates the ring. And so I can do the nitration here at 50 degrees 1 hour. To get the second nitration, I have to heat it up to 70. And the third nitration, I've got to use fuming nitric acid, 120 degrees, 5 hours. I've got to really wail on this thing to get the third nitro because this is highly deactivated by the two nitro groups already. So when you're adding strongly deactivating groups, very easy to stop after the first one, the second one, of course, the third one. This is what? This is a compound you know. That's TNT. That is trinitrotoluene. That's the explosive that is used for industrial purposes, bombs and so on. So yeah, so you can nitrate toluene either one time, twice, or 3 times just by modulating the reaction conditions. And we've reached the end of our hour, so we'll pick up